Hey everyone, welcome back to the shop. So this is an update and a sort of progress report on this project I've been working on for the past couple months, and that is to build a scanning white light interferometer here in my kitchen shop for the inspection of surface roughness down to sort of single-digit nanometer level. First off, before I get into it, big thanks to everyone who left comments on the last video I did on this where I was asking for help with some of the problems I was having. I'm generally extremely proud of the comment sections under my videos, and that was a good example of why. I have a very, I think, productive and sort of positive environment in the comment section, and I like to keep it that way. I think that's just a consequence of being small, but you know, I'm quite thankful for everyone who left comments and advice on that video. Special thanks to Patrick, MSDS, and Epic Jr. Specifically for working through some of the problems with me. Anyways, a little bit of background on this. Why am I wanting to build this? Well, this is still tangentially related to the diamond turning lathe project. As with all precision machining, the metrology is as, if not more, important than the actual machining itself. So with diamond turning, there's really two main areas of metrology that we need to consider, and that is form accuracy and surface roughness. So the form accuracy I've covered a little bit in my experimentations into building a bath interferometer, and that's an instrument which gives me global form measurements of how accurate the surface is over the whole clear aperture of whatever optic, or spherical optic or nearly spherical optic that I'm making. I'm working on a Fizeau interferometer for simple flat optics, but that basically covers most of my bases for form measurement. Roughness is the other thing that I need to find a way to measure. Typically this is done with a profilometer in most machining applications, but with diamond turning and the surface roughnesses being as small as they are, and people also generally wanting a little bit more information than just a simple line trace out of the measurement, we turn to something like this, coherence scanning interferometry, which is a non-contact sort of 3D aerial surface roughness measuring technique. And like I said in my previous videos, I'm not going to get too deep into the theory behind it today, because that's been well covered by Huygens Optics. Go watch his video on it if you want to get a refresher or be brought up to speed. But yeah, that's basically why I want to build this. It's because I want to know what the surface roughness of something like this is. And that's generally a difficult problem to solve. So first I'm going to go over the physical and optical setup that we have going on here on the bench, because it's changed quite a bit from the last time I showed it. And then we'll look at the software and sort of take a deep dive into what I've been experimenting with and what I want to continue experimenting with, some of the results that I've gotten thus far, maybe how we can improve a little. Hopefully it will stimulate some more productive discussion in the comments, but that'll be a little more in the weeds, so I'll save that for the latter half of the video. But first, let's look at the optical setup here. It's really quite simple. So anyone familiar with the Michelson interferometer can sort of discern what's going on here. That's the type of interferometer setup I have going on. There's of course different ways of doing this. For interference microscopy, there's Moreau objectives, there's Linux setups where you have two identical objectives being the two arms of the interferometer. But anyways, getting distracted here. The main upgrade from the last video is we have this nice fancy new objective. It's a 4x apochromatic. Modic is the brand. I think it's a clone of the Mitutoyo, but it's a much needed upgrade from this kind of crappy single element 4x objective I was using before. You can see the size difference there. Now, that improved the image quality a lot, which is always a benefit, higher spatial resolution now. But it's worth noting my image quality is still not stellar, because even though I have this relatively decent quality objective, what I've done is I've gone and stuck a glass cube right in front of it, and that objective is not optimized to deal with an optical element, basically a parallel, right in the optical train like that. So this absolutely does induce some aberrations. It's not terrible, but it's worth pointing out that there's a reason that an interference objective is typically just a thing you buy, with the cube being built into it, or in the case of the Moreau objective, the plate beam splitter, it's all built into it, and everything is corrected to operate with this optical element in the path. This is not that, so this is introducing some amount of aberrations. So the other nice thing about this objective is it's infinity corrected. So I have infinity space to work in back here and introduce my light. But because it's infinity corrected, I now need a tube lens, and that's what this assembly is here, this 3D printed telescope looking thing. There's a little achromatic doublet in the end of that, and that's serving as my tube lens, and that works all right. On the illumination front, I'm now using a plate beam splitter here to bring in my light, which is quite the upgrade, because before I had a cube beam splitter here putting the light into the optical train, and that was not the best choice because these are pretty cheap cube beam splitters. They don't have any anti-reflection coatings, and so I was getting a lot of back reflections from the flat faces on the front and back of the cube, and that's basically entirely eliminated with a plate beam splitter. The light levels I'm working at they're pretty low from an intensity standpoint, because here the intensity split in half of it's lost. Here split in half again, and then it's split in half again once it goes back in, and then split in half one more time as it passes through the beam splitter, the final pass. So even a little bit of back reflection from the interface between the cube beam splitter and the air was sort of washing out the signal, but this basically eliminates that. My light source is just a microscope objective held in this 3D printed mount with an LED sitting right here, and this LED has actually been, I don't really have a great way of showing this, but it's been cleaved, so like the dome part on the top has been cut off, and then I've lapped it all the way down to the chip itself. So it's really just a bare LED chip acting as a quasi point source, and then this microscope objective roughly collimates that. I went on a whole sort of, not rabbit hole, but I went chasing very good spatial coherence for a long time, because it was my understanding that was necessary to achieve interference. But it's become obvious since then that you do not need a spatially coherent light source here to get fringes. I thought you did, but I've done everything from, have a tiny pinhole here and have a really nice point source, to just shining a flashlight, to literally holding an incandescent light bulb generally in this vicinity, and I get fringes. As long as it's lined up, I get fringes every time. So clearly I was sort of misguided on the spatial coherence thing. So maybe someone can explain that, but yeah, not necessary, I guess. So despite these upgrades, illumination is actually still basically the limiting factor in this current setup. Basically because whatever setup I have going on here, and this is partially the fault of the very low numerical aperture on the objective, but I'm just not getting a even illumination, if you will. That's probably not the right word. Basically, counterintuitively, what I want is a very low contrast on the image that I'm getting back. And basically what I mean by that is light sort of everywhere on the surface. Like, I don't want scratches and pits to have contrast so they stand out in the image. I want those to be well lit sort of all over as best as possible, so that I get fringes everywhere. And even though I can't see those, that means I can't see those features in the image. They will show up in the interferometer signal and be in the final height map results. So we'll look at some data later, sort of showing the issue, but there is an illumination problem. You know, having this perfectly collimated is not doing it. I've tried a couple other, you know, levels of diverging and converging illumination, and it's not really not satisfactory yet. But like I said, we'll look at that a little bit later. So let's look at the actual sort of opto-mechanical front here. As I demonstrated in the last video, PLA, not good. We know this. This has been established. But basically, most everything is just passive to, you know, hold components in the right position here. But the upgrades I did I made this little translation stage, and this is mostly 3D printed, but it's built off of one of these micro linear rails here to provide a axis of motion for the second arm of the interferometer. As I showed in the first videos on this, this Parker stage over here is still providing the scanning motion back and forth, but just for alignment, having this linear axis, and then you can see I got this tiny little tip tilt stage on eBay to provide adjustment in the angular directions. This has made things a lot easier. It was really challenging before, and it still is pretty challenging from an alignment standpoint, because consider not only do the sort of two faces of the two objects you're measuring have to be angularly aligned extremely well, the lengths of the two arms of the interferometer need to be matched almost exactly to within, depending on how good your angular alignment is, you know, maybe a couple microns or so. So this is challenging because you adjust the angle and your arm length changes. So you need a way to sort of be able to really easily manipulate those degrees of freedom. And before, I was literally just tapping stuff around with an Allen wrench. So this is a huge help and makes setting up and actually getting fringes much faster. Now, as far as which arm is the reference and which arm is the sort of test or sample arm, I've gone back and forth on that. So in this current configuration, this is the reference arm. So this little prism here, this illuminized prism, this is the reference mirror, if you will. I'm basically just using it as a pretty flat, very low roughness reference mirror, right? So that would mean the sample would be held on this tip tilt stage here. Right now that sample happens to be a ball, which is why you see a big ball here, but typically it would just be, you know, something glued or taped to the front of that stage there. This is an illuminized mirror, like I said, so it has a very high reflectivity. Matching the reflectivity of the two objects in the two arms of the interferometer is very important for good fringe contrast. So if you're looking at sort of a uncoated glass surface on your sample arm, this is not going to work at all because the reflectivity of this is so much higher that you won't be able to discern any fringe contrast in the resulting image. So I use this for some stuff, and then I've got a chrome coated piece of silicon that has a slightly lower reflectivity, which is better for some things, and then this just uncoated glass flat, which is good for very low reflectivity things. And these are just three flat reference surfaces with varying levels of reflectivity, essentially. Now, to explain the decision between which of these arms is the reference and which of these is the sample, traditionally, your reference arm would be the one sort of at 90 degrees to the optical axis and fixed, and then the objective is scanned where your sample would be here, right? This actually ended up producing much worse results in my particular setup, and that's just because the poor optical alignment of all of these things literally just sitting here on the breadboard. So what would happen is, you know, if you imagine the roles reversed and we have, say we're looking at this block here, and we shift this through focus, what happens, because everything's not super great aligned, is as that translates and moves in and out of focus, there is also some lateral shift of the image on the sensor. And that's really bad, because then your height data for one pixel is basically moving to adjacent pixels, and your data set for a single pixel is interrupted and basically replaced with adjacent ones. And that, it's kind of hard to explain, but it ends up making a noise nightmare for the actual data processing. So having a very stable image of the sample you're looking at is important, and not hard to do if everything in this setup is perfect, but right now it's not. So it's easy enough to reverse the roles, have the sample there, have your reference here, and because in theory, right, your reference arm, your reference surface doesn't really have any information in the XY direction, we don't care if the image of that shifts left, right, up, and down, because there really is no information there. The other difference between this setup and a commercial one is they typically use piezo stages for the actual scanning motion, and this can get extremely smooth, sub-nanometer precision motion. Whereas this Parker stage, it only has a resolution of 10 nanometers. The way I combat this is scanning at a constant velocity, a very slow constant velocity, and then just sort of subdividing in time to get this height steps, rather than trying to move a discrete step and then take a picture and then move a discrete step and take a picture. I do have some piezo stages that I've been experimenting with and playing with. That'll probably be a future upgrade, but for now I'm not actually really observing the stage performance limiting any of the quality of the images that I'm getting out of this. So we'll see when that upgrade comes. So now we're going to talk a little bit more about the software and the data processing approaches that I've been trying to produce the 3D data from the fringe videos that I record. So before I do that, though, it's worth reiterating one more time what the fundamental problem with the illumination is, and there's really no way you can solve this with software. There's lots of different approaches to doing the demodulation and the height reconstruction from the data, but if you don't have fringes for a pixel, there's nothing you can do about it. You simply don't have height information for that pixel. So, like, for example, this is this microscope image here of a lapped steel ring gauge. You might consider this image fine, but the problem is you can see the scratches. They're dark and they have contrast. So what happens is when we start to scan the mirror, the reference mirror, and the fringes move across the surface, this looks very nice, it's very pretty. But you can note there are some places in like the depths of the deepest scratches in the darkest places where the fringes are not causing an intensity modulation for that given pixel. The pixel remains dark or almost dark the whole time. And that's what we can't get around with our software. And that's what needs to be solved basically purely with optical means. I need to improve my optical setup. Perhaps a higher dynamic range camera could also help with that problem, but I don't really have the money for a really nice camera right now. So anyways, there's, as I said, lots of different approaches to doing this. I'm going to break down sort of a couple of the ones that I tried, and a couple of the different methods, and show some results from each of them. But fundamentally, this is the signal for one pixel, right? We start scanning, and as we reach this point here for a given pixel, this is the point where the two arms of the interferometer are of equal path length, where there's maximum fringe contrast. We get sort of no signal, and then there's a little chirp of interference fringes, and then it goes back to zero. And our task is basically to determine where this point of peak contrast occurs in a range from the start of our scan to the end of our scan. Here I have it just as 20 microns because it's, for most of the pieces of data I recorded, that was about the total range that I traveled. And the precision with which we can basically locate this chirp inside of this 20 micron window is the precision of the instrument and how good of a height resolution we can have. So the first thing I tried, just the most basic approach. MATLAB has a built-in envelope function, and I just said, let's take the envelope of this data set, find the max, and call that our height value, right? That does not work really great. Those are the results that I showed in the very first video I posted about it. That was this data I showed of the ground steel block. Really noisy, several microns of just kind of crap, no real discernible surface to make out, a couple little pits, but I would not call this good. Now, it's worth noting that part of the reason this was so bad was also because this was back when I was using the MP4s for the data file. I would record the raw video, and that video comes out as an AVI. And that's the full, I was doing that, the full frame of the camera sensor. But then, because my camera sensor is almost 4,000 pixels wide, and that would take literally days to process with my current methods, I would put this into a video editing software, basically reduce the resolution and save it as MP4. And this compression really wrecked my results. Did not do good things for it at all. Unfortunately, though, what I've had to resort to doing instead to avoid this problem is really just subsampling the image sensor. So instead of taking a full frame video and then reducing the resolution, what I do is I just record the original video with like 800 by 800 pixels worth of the sensor. And so this is not ideal because I would like a wider field of view for a lot of things, but the resolution of the camera is too high. So for now, I've just basically cropped the field of view, and I'm looking at a much more zoomed in image. So anyways, the next thing I tried was an idea brought to me from Patrick, a viewer who reached out. And basically the suggestion there, there was two things I took away from it. One was the way of finding the envelope. The MATLAB envelope function uses the Hilbert transform, I believe, or some version of that. What he suggested was, you've got this signal here, basically treat it sort of like an AM demodulation. So multiply this by a sine wave with the same frequency as this chirped sine wave here, and then in the frequency domain it basically shifts the envelope functions to the center, or to the end, to the low frequency end. You can then cut everything off with a high or low pass filter, IFFT that, and then get your nice envelope back like that. That's what we want, right? Is something nice and smooth there. And that method for finding the envelope ended up being a little too computationally intensive. But what was more interesting was the next thing he suggested, which was, instead of just finding the peak, because in reality, the envelopes never looked this smooth. They were and the data also didn't look this smooth. There was a lot of noise sort of on top of it. So just finding the peak might put you in the wrong place. He suggested finding the center of mass of the envelope, or the centroid of this shape, basically the weighted average of all of the data points on this line here. And I thought that was really clever. And so I tried this for a few different pieces of data, and this ended up getting really nice looking results. Nice looking is the key point there. So the noise levels went down a lot, and I was actually starting to make out some of the real texture in the data. The only problem with this method that I didn't realize until later on is that the accuracy of it is very dependent on the signal to noise and how good the fringe contrast is. So in a pure theoretical sense, if you just have this nice clean pulse right, and nothing else going on, and you take the center of mass or the centroid, you will get the peak, right? So that should be great. And if it, if your envelope was something like this and it was in a different location, it would find that pretty accurately. But if you have any noise sort of over here, right, that might not affect the accuracy for this given pixel, right? We might be able to find the center pretty good if this is relatively consistent on either side. But let's say the next pixel is different and it has like a different amount of noise, a higher amplitude of noise, or really just worse fringe contrast. The amount that the intensity of the pixel is being modulated by the interference is sort of on the order of just the noise of the pixel. Once this noise starts to become a significant portion of the amplitude of the envelope, that starts to carry real area under the curve and bias the center of mass in one direction or the other. And so it turns out that because of this sensitivity, you can get varying levels of performance within one image that you're trying to look at. And the height information you get back, sometimes it has low noise, but it isn't necessarily accurate. Like the value that it will spit back out at you for wherever the center of mass is not necessarily correspondent with the peak of the envelope, which is where the true the true height value lies. So I started thinking about ways to deal with this, and the first kind of cheap and easy way to do it was I just squared the data for all the pixels. And so what that does ideally, right? Well, first of all, it makes everything positive, and so your envelope ends up looking something, or not envelope, but signal ends up looking something weird like that. But the other idea was, because we're squaring it, it does this sort of non-linear scaling in the y direction, and hopefully it brings the amplitude of the actual interference fringes sort of out and draws them away from the noise, which is small, so it isn't scaled as much, and basically just stretch the graph in this direction and have more area under the curve for the parts where there's actually fringes, so the center of mass is more biased towards the actual modulated signal there, rather than biased by area under the curve just from noise. And that helped, but it still wasn't. I wasn't happy with the accuracy. It was not really 100% of the time giving me what I thought to be the true location of the fringe contrast peak. So I looked at a different method, and that's the one that I'm still using now. The way that method works, funnily enough, is we start by doing the same thing. We square the signal, and so we get something that looks like this. The thing is, though, when we square it, it does something kind of cool, similar to the AM demodulation technique. And just to explain that in a little more detail, what I was trying to say, when we take the Fourier transform of the pulsed or chirped signal that we get out of this, well, for one, we get the spectrum back of the light source that we use, which is kind of cool. And usually, well, that's not very Gaussian, but we get something that looks roughly like this. And it's got, a spectrum of frequency components that make up this chirp here. When we square that, the unique thing that it does is it shifts this Gaussian pulse to 0, or about 0. It changes it out here too, but it does. And remember, it's symmetrical, right? So we'd have the other half of it here, which I wasn't showing before. But it takes this and it shifts it to 0. And then we don't care about this part anymore. We low pass that, so we get rid of all this, and conversely all this, and then take the inverse Fourier transform of this stuff that's been shifted back to DC here, or around DC. And the inverse Fourier transform of that is that nice envelope we wanted. So super cool. And it turns out that this is a very, very computationally efficient method for getting the envelope. And that's the method I've been using. So it's nice and fast. It is reasonably accurate, but to improve the accuracy even further, I've taken it a step further, done one other trick where we have a reasonably accurate envelope here, and it's nice and smooth. And the nice thing is we can control the smoothness. But if we just take the max, it will do, a peak search algorithm, whatever it uses, and it will find the data point within this envelope that has the maximum value. But the resolution, this is a discrete data set, right? So it only has a resolution of however far we moved in one frame of the video. And for most of the videos and stuff, it's like 8 nanometers or whatever. So that's not a crazy high resolution, and we can do better than that. So what I do is I do a peak find. So I find the maximum value of the envelope. Then I take a small window about either side of the peak, and we just look at the data that's in that window. And I actually do the center of mass calculation within this window. So not a global center of mass, but find the maximum and then find the centroid of everything, say 10 frames on either side of that max. And so that averaging gets you a much higher resolution, and hopefully my thinking was a slightly more accurate max peak find to begin with. So that's what I've been using. Gives a little less noise this way. Nice, true, accurate data because it's based off the max of an accurate envelope, and it's nice and computationally efficient as well. And that is a huge problem with this white light interferometer algorithm business, because consider the scale of the data we're dealing with here. If you have a 480p video, historically we call that a pretty low resolution video, that's got over 300,000 pixels, and if each pixel has its own data set, for some of the videos that I took when I was scanning nice and slow, they had 1,000, 2,000 frames. And we have to do this processing that I've just described, this algorithm, for every one of the 300,000 pixels. So, you can sort of see how this could be a problem if your algorithm takes any reasonable amount of time to execute. If it takes 20 milliseconds to do whatever you're doing, and you have fancy smoothing and you're doing all sorts of cool tricks to get a really accurate peak finding, that's great. But if it takes 20 milliseconds, that's an hour and a half that it's going to take to process your whole image and give you your height data back. And that, unless you have some way of doing it in parallel or whatever, but that's beyond my pay grade. So yeah, that's the algorithm. Let's take a quick look at some of the results I got. So I think I showed this in the last video. This is an example of the real data for one of the pixels, with an envelope applied to it, a pretty coarse envelope here. But you can see how it's not actually a nice Gaussian chirp because of the non-Gaussian spectrum of the LED light source that I'm using. And that was an example of a nice, highly contrasty pixel. This is the opposite. So this is the data from a pixel that had very poor fringe contrast, and you can see it's very hard to make out the interference pattern beyond just the noise of the intensity of the pixel. So these are the ones that are really hard to deal with, and it's hard to come up with an algorithm that doesn't freak out on pixels like this and gives you something even in the ballpark of correct. So that's what we're trying to avoid. But anyways, let's take a look at a couple things, and we'll do this in chronological order. This is a lapped carbide surface, which was one of the first decent results I got with the centroid method, the center of mass method, and the noise levels are much less than that first gauge block that I showed, but I don't really trust the amplitude data for just as far as it's like absolute numerical value. and you can see you've got these nasty spikes wherever there's pits, and those are from where we have poor fringe contrast. And basically, when we don't have enough fringe contrast to find a good envelope and to find an obvious peak, it's basically just guessing when it does, like whenever we do the max and try and find the peak or the center of mass, it just ends up in a random position, and so we get kind of a random height value, and that's what these spikes are from, are just poorly contrasting pixels. So this is the diamond turn acrylic surface that I tried next, and this was one of the first results where I was really pleased with what it gave me here. You can see really nice clear tool marks and like what looks like really good height data for that surface. And the reason this looks so much better than the other results I had been getting is because this was an example of something that actually had good fringe contrast pretty much everywhere on the image. So you can see in the video here, even when I go back to before there were fringes, there are dark spots in the image. These are the valleys, right? And they are darker, but as the fringes start to move through, those dark areas, they're still getting modulated. Their intensities are being modulated by the fringes there. So there was no basically dead zones from a data standpoint, and we got nice clean height data for most of the surface, except for these speckles of dust that were left around. So next, this is a AFM sort of reference sample standard thing for calibrating AFMs, and this was the first good result I got with the most current method that I'm using, with the FFT based envelope detection and the windowed peak finding thing, and so this is where I was starting to actually become finally satisfied with what the instrument was putting out. So these lines are, I think, 15 microns wide and about 100 nanometers tall. So, just to give a sense of scale, that's a pretty small step height. And you can see on the silicon substrate, which is what this is built off of, the actual noise. And I'm assuming it's noise. At this point, maybe it is actually the roughness of the surface, but I'm kind of assuming it's noise. That noise floor was starting to get down into the low single-digit nanometer RMS range, where I was starting to really be happy with the resolution limit of the instrument. So this is a pretty neat result to get for something built in the kitchen. And then finally, this is the ball bearing you saw mounted on the interferometer earlier. So this is sort of cool. You can see the obvious curvature of the bearing, and then there are some dead spots where we didn't get good fringe contrast. If you look at the actual video here, here's that image, and you can see the fringes coming in, and this is just so beautiful to watch. But you can see there are some areas around the edges of these pits over here that do not have adequate intensity modulation from the fringes. And that's why those areas look like that. But down here, these long scratches and grooves in the bearing, those turned out great. You can see that's here and here, where we had nice contrast all over, or lack of contrast all over rather. And we have a really good recreation of the height there. So this peak to valley is around 4 microns on this image, and so those grooves there are extremely shallow. They're also around 100 nanometers deep. So yeah, that's pretty much it. I'll keep working on this, and like I mentioned, there's a couple other methods I want to try for the data analysis. I'm not going to go into it right now because this is it's too much information. This video is a pain in the butt to make, just trying to find a way to parse all of this into something that was remotely presentable, and even still, I've just been spewing word salad for this whole thing. So hopefully someone found it interesting, but I'm not really in the business of making videos with mass appeal, so don't mind that too much. Anyways, hope you found this interesting. Please do let me know if you have any questions. I'd love to chat about this stuff some more with you, and thanks for watching.